In this video, we'll see how to compute the gradient of the loss function with respect to the parameters of the log unary factors in a conditional random field. So, we are deriving the stochastic gradient descent training algorithm for a conditional random field, a linear chain conditional random field. We've seen the loss function before, and now we're going to start looking at how to compute the gradients with respect to the different parameters of the log linear conditional random field. So before, we've defined the loss as the negative log of the probability of the true label sequence given the input sequence. So now let's look at the gradient. All right, so we'll focus now on the gradient with respect to the unary log factors. That is AU of YK prime, where YK prime can be any class label. So it's not necessarily the observed class label, it's for any class label. So the partial derivative of the negative log of the probability of a given sequence Y given some input sequence X with respect to the unary factor for some arbitrary label Y prime at position K is going to be actually quite similar to the gradient of the pre-activation at the output layer of a neural network. It's going to be minus the identity function of whether yk, so the kth label in y here, is equal to y prime k, which is the label for which we're considering the parameters of the unary factors, minus the probability, according to our model, of actually observing for the kth label the actual value y prime k for the given input. So again, we have this formula which is essentially minus what we would like to see, which is what we actually observe, which is a label of yk, minus what we currently predict. So we have essentially a term here which is only one when we're considering the unity factor for the correct answer, minus the probability distribution of the current value of the parameters of the conditional random field for the kth label. Okay, so that's actually quite similar to the neural network pre-activation value at the output layer for classification that we've seen before. So if we consider the specific case of a conditional random field where we have, for a given context of radius 1, 3 different neural networks, one that computes some pre-activation based on the current position, another one based on the input on the left, and another one based on the input on the right. So we consider the gradient with respect to all of these pre-activation function at the output layer of these 3 neural networks. That would give us the following gradients. It would be minus the one hot vector with a 1 at the real value of the label at position k, minus the vector of marginal probabilities for what the label might be according to the current conditional random field for position k. So that's for the neural network that looks at the input at the current position k. And if we're for the one that's looking on the left, well, the gradient is going to be 0 if k is equal to 1, so if it's not greater than 1, and that's because and for k equals 1, there is no neural net trying to predict from x0, since x0 doesn't exist. And similarly, we have also an indicator function for the one that looks to the right, so that the gradient is 0 if k is equal to capital K. So now let's look at the derivation for this formula so let's try to see why this is true. All right, so we're looking at the partial derivative of the negative log probability of some vector labels y given some input x with respect to the log factor, the unary log factor, and its value for some given label y prime k. So k, it means we're looking at the position k in the sequence, and y prime k would be some value between 1 and capital C. So here, the only thing I've done is just write what is minus the log of p of y given x for a for a linear chain CRF. So remember, we have the log of the exponential of these terms, so we just have these terms once we apply the log, minus the log of z, because before we had divided by the partition function, so the log of that would be minus the log of the partition function. Now, the gradient of this, the partial derivative of this whole expression with respect to that term is going to be 1 if the kth label is actually y prime k. Otherwise, that particular expression is not going to appear here. Okay, so the gradient for any other position than k of these terms here is 0. The gradient, the derivative with respect to that, with respect to this is also 0. So it's only the case for the same k, which is important. And if yk is equal to y prime k, then we'll have exactly the same term. So the derivative of that is going to be 1. Otherwise, it's going to be 0. And then minus the derivative of the log partition function. So we'll just apply the derivative to this minus the derivative of that. So let's do that specific term, the derivative of the log partition function. So the derivative of the log is just 1 over that, 1 over z, times the derivative of whatever we're taking the logarithm of. Now here I'm just writing the expression for the partition function. So because I've used the symbol y prime k, I'll use instead y prime prime for referring to the sequence over which I'm taking the sum here, the nested sum. Now I can push so the derivative of a sum is the sum of the derivative, so I can push the derivative inside here, so right here. So that's what I've done right here. And now the derivative of the exponentiated sum of factors, or log factors, well, if here au y prime k does not appear, then it's 0. And it won't appear if y prime k is not equal in the sequence y prime is not equal to y prime prime k. In the sequence y prime prime k, if at the position k its value is not the value of y prime k, then the derivative of that is going to be 0. Because it's going to be constant with respect to that variable. However, if it does appear, then the derivative of the exponential is the exponential itself. So it's going to be that term, and times the derivative of the argument, well, it's just going to be 1, much like it was 1 right here. So essentially what we'll get is the indicator function of whether y prime k is equal to y prime prime k times the exponential of the sum of all log factors. Now let's notice that here, that's the numerator of the probability, the conditional probability in the conditional random field. And that's the partition function. So I can just remove it here and just divide by it here. And then what do I get? Well, I get that this whole term here is just the probability of observing as the sequence of labels y prime prime 1 followed by y prime prime 2 up to y prime prime capital K, and then this term here is here. And now if I take the sum over all possible sequences of and I only consider the terms where in all these sequences, I won't consider the sequences such that y prime prime k is equal to y prime k, then I'm just summing the probability of all sequences which satisfy this condition. So all sequences such that the kth element in the sequence is y prime k. And so the sum of all of these joint probability is just the marginal probability that y prime k is the kth label in the sequence. So I do obtain that this term here is p of y prime k given x. And so I do have that the gradient, the partial derivative with respect to the log unary factor, is the indicator function minus the probability under the model. So So that's great. We now have the gradient or and the partial derivative with respect to the log unary factor, but we don't have it with respect to the parameters in the log unary factor. Fortunately, we've seen that the backpropagation allows us to very efficiently apply the chain rule and backpropagate the gradients to all the parameters. So essentially, from the parameters of the log unary factors, that gives me essentially the partial derivative with respect to the pre-activation values at the output layer of the neural nets inside the CRF, and then I can just take those gradients, those partial derivatives, and backpropagate them towards all the parameters of the model. Now notice that because it's the same neural network at each position in the conditional random field, I need to accumulate all the gradients for every position in the sequence. So all of these gradients need to be accumulated into my computation of the parameter gradients. So let's look at the specific case of a linear chain conditional random field. So the case where the log factors are linear. So this would be the neural network from the center, the computation that looks at the aligned input. So it would be linear transformation plus bias. Then we have the computation that looks at, I'm sorry, that's a mistake. That should be, oh no, sorry, yeah. So that's one way of writing it. I could have written it k minus 1 here and k minus 1 here. I could have written k plus 1 here, k plus 1 here. But let's just assume now that we have this log linear model where the unary log factors are just linear function of the context window. So in this case, the gradient with respect to the bias, and also I just want to say that notice I didn't put a bias here or here, and that's because I would just be redundant since having just a single bias is sufficient. So the gradient with respect to the bias would be the gradient with respect to the pre-activation function for the center of the window, but summed over all positions. So that's the gradient of the pre-activation function at all position k, so for all inputs xk, all position k actually. And we've seen before that the gradient was essentially this, the one hot vector minus the vector of marginal probabilities for position k. So I'm just summing over all positions k. And now if I want the gradient with respect to the weights that connects the input that's at the current position k, or that's to the left or to the right, well, I get something that's essentially very similar. It's again the one hot vector minus the vector marginal probabilities, but for this part of this parameter matrix, I multiply by the transpose of the vector aligned with the current position k. This one I multiply by the vector to the left, the transpose of the vector to the left, and the transpose of the vector to the right.